Hello everybody, welcome back to another Gregorius Maths video, and today I shall be continuing on with my homological algebra series. And soon after the first video I realised that it was pretty stupid that in my plan I put categories and functors so far ahead in the series when really they should be straight after the introduction. And so today I'll be talking about categories and functors. And the reason for this is simply because throughout the rest of the series, we will be talking in the language of categories and functors. Now, this won't be the most exciting video, but it's necessary. And thankfully, I pretty much just copy-pasted my notes from last year when I had to write out notes for the exact same topic, but in the context of homotopy theory. Which was a relief because I really did not want to rewrite these notes. So there's a little bit of motivation for you, Gregorius motivation. Put in the work now so that your older self will thank you. Anyway, categories and functors. So here we go. It says here in the notes that we'll be talking about colimits, but if they come up, then I guess you'll just have to cope. You'll just have to look up what it means. I will just be looking at categories, functors, natural transformations, and adjoint functors as well. So, firstly we should talk about what a category is. Now, there's plenty of motivation for studying these things, but I will not be discussing any of that simply because this is just a video explaining the language that we're going to be using in videos to come. And so I don't really want to motivate anything. That's, if I were to motivate it, it would be for category theory series. So I won't be doing that. So anyway, definition. A category, we'll call it C, consists of the following information. So firstly, we have a set. Or maybe, okay, I won't call it a set because that's probably imprecise. I'll call it a collection. A collection of objects, which is denoted by C. And we also have ways of mapping between these objects. So those are called morphisms. So for any two objects, if we have A and B in the set of objects of C, we have this set Hom C A B, and what this does is this is the set of all morphisms between them. So that is maps from A to B like this, and morphisms can be composed. So we have a function which looks like this, composition, and it takes in a functor between, a morphism between A and B, and a morphism between B and C, and it outputs a morphism between A and C. So this, let's say this map here is F, this map here is G. Well, this would get mapped to G compose F. I'm doing maths correctly. Yes. So diagrammatically, we could look at this A, C. So we have F here, we have G here, and this map going straight across, that is G composed with F. Now, this composition has to satisfy associativity. So if we do if we do F compose brackets G compose H, let me write this down. If we do F compose brackets G compose H, that is the same thing as doing F compose G, and then composing that with H. And there must be, for every object, for A in the objects of C, we have an identity morphism, so we call that 1A, and this is in so this is a map from A to A, and what it does is for given any B, so for all B now, we have so we'll call B an object in C, and then for all F in this Hom set between A and B, we have that F composed with 1A is equal to F, and similarly if we have F in Hom BA, we have that 1A composed with F is equal to F. Okay, so this is the information that a category consists of. So basically it's just objects and morphisms which satisfy a bunch of rules like composition and stuff that we're already familiar with. So just to clear this up, I'll give a few examples now. So for example, the category of small sets. I'm not exactly aware of the foundational issue which caused me to write down small, but maybe there's some size issue if we include all sets and parallel. I don't know. I'm not into that sort of stuff. But the category of small sets, which we denote set, so the object is sets, and the morphisms, we'll just denote it by more, is equal to functions. So that's normal. We have sets and we have functions between those sets. Now, similarly, for group, we have that the objects are groups, and we have that the morphisms are homomorphisms, as we would expect. Similarly, we have topological spaces, rings, modules, manifolds. What other funky examples have I written down here? Yeah, we've got smooth manifolds, pointed topological spaces. Yeah, I've got a little bit more of a homotopical example here, but I'll leave that out since this isn't the aim. There's also quite an interesting example where you can describe a group as a category with one object. So we'll describe, given a group G, the category BG consists of one object, and Hom in this category between this object is just G. Now let me explain. So every single morphism is an element, and the composition is the so F from star to star, this is actually just an element of G. And then F composed with G is just FG. So that's just what a group is. It's just a category with one object. And the morphisms are the elements, and composition is the group operation, which of course satisfies the axioms. Actually, sorry. I misspoke. This is a monoid. However, if we make it a groupoid, that is every single morphism has an inverse. Right, yeah, I've somewhat made an error in my notes here because I've written this category, but I should have said that this should be a groupoid, which means that every single morphism is invertible. So that would correspond to there being inverses in the group. So what I've described here is a monoid, because we don't need inverses in a monoid. But so a monoid is a category with one object, and a group is a groupoid with one object. Where again the morphisms are the elements of the group, and the composition is the group operation. So, okay, that hopefully you've gotten a flavour, just a few examples of what categories are. Also an interesting definition which might pop up here and there is the definition of an opposite category. So given some category C, C op is precisely just, it's got the objects are the same, so let's just Right, so the objects of C op are precisely the objects of C. All it does is it reverses the arrows. So if we have hom in C of AB, this is simply just the arrows going the other way in C op. So that's just a nice and simple definition. It can be convenient, sometimes sort of duality type stuff, you know, whatever. Somewhat convenient. Okay. Right, yeah, okay. So within these categories, so for example groups, this is not really all the information we want to encode. We also want isomorphisms, because in groups we want isomorphisms. In set, slightly less clear why we'd want isomorphisms, but for example in topological spaces we study, we kind of consider two spaces to be the same if they are homeomorphic. Now if you want to study homotopy theory, then I guess you could introduce a kind of weaker category wherein the isomorphisms would be homotopy equivalences. I guess similarly for homological algebra you could do that with quasi-isomorphisms. So there's all sorts of different isomorphisms that you'd want. Some of them you can just get straight away from the definition, sometimes you have to be a bit more creative. But this isn't all the information we want. We want to encode what is an isomorphism in this context. And the way that we do this is, as you would expect, just two objects are isomorphic if there's just an inverse. So we have a map called an isomorphism and it must have an inverse. So given two objects C and D of our category, we say that C is isomorphic to D if there exists blah 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 some F between C and D such that there exists a morphism G from D to C such that G composed with F is equal to the identity on C. Is that correct? Yeah. No, what? It's equal to the identity on D. No. Yeah, identity on C, and F composed G is the identity on D. So, again, let's give some examples of what this would mean. In set, a function has an inverse if it's a bijection, and it's a bijection if they have the same cardinality. So in set, looking from a categorical perspective, two objects are the same, two sets are the same if they have the same number of elements. In group, homomorphisms, so for a homomorphism to have an inverse, that's pretty much just the definition of a group isomorphism. In topological spaces, where the morphisms would be continuous functions, of course again we've just described a homeomorphism, etc, etc, etc. And yeah, let's see if I've got any other funky examples. No, okay, I don't have any funky examples. Alright, so that's basically the ins and outs of categories. Now let's move on to functors, which is how we map between these two categories. So, might as well define what a functor is. Covariant functor, right, yes. Definition. So, let's have two categories C and D. A covariant functor. Sometimes people leave out the covariant part and just call it a functor. So a covariant functor, or just a functor, which is denoted almost exclusively, unless we're talking about a special functor here, with F, capital F, from C to D, satisfies the following properties. So keep in mind, we have two bits of information we have to map. First we have to take the objects to the objects, and secondly we have to take morphisms to morphisms, and it just has to do so in a somewhat convenient way. So for example, so the first, I made a little typo here. So for some objects C, in the objects of the category, we have the F of C is in the objects of D. Now, for any f in Hom C of AB, f of f is now a functor not in C, but it's a functor. It's a morphism between two objects in D. So f of f is a map between f of A and f of B. And remember, f of C is just an element of the objects of D. Okay, and right, yeah, it has to satisfy the following property, which is that under composition nothing happens, so f of G composed f is just f of G composed with f of f. And yes, it has to preserve identities too. So f on the identity is just the identity on FA. Since of course f is mapping this is still a morphism, right? So if we look at it in terms of here, if we replace 1A, this is Hom C of A, so f of A must be in Hom D of FA, and the identity must be mapped to the identity in this one too. That's what that's saying there. Okay, good. So that's what a functor is. Now, we also have a contravariant functor, and it's very similar, except it takes morphisms the other way. So for example, f of f now, if we're defining covariant, these two guys would be swapped. I'll say purple. Contravariant, sorry, what am I talking about? Covariant, I'll just define the covariant. Contravariant. Right, yes. So if we swap these two guys around, we get a contravariant functor. And of course, similarly here, we'd have to swap these two guys around. And the reason for, so if we think about it, if we're taking in an f, and it's going from A to B, the contravariant functor, what it's doing, is it's going from f of B to f of A. So it's flipping it. That's what contravariant functor means. And so when it's not specified, functor simply refers to the definition in blue. So if we go back to the blue pen for a second, I probably should have chosen a colour that's a little bit more distinguishable, but whatever. F of f would now be going from the way you'd expect it. Like that. So that's okay. That's the definition of a functor. Now there's a lot of examples of functors. For example, the forgetful functor is the one that just forgets structure. So for example, if we go from abelian groups to set, forgetful functor will map the objects to the objects, except will just simply discard the extra structure, the addition operation. It'll just discard that. So it's forgetful. Again, a functor, so going back to this group analogy, let's test this out actually. This is quite a nice way to understand the definitions. If we now apply the functor definition, well, what happens to f composed G? F of f composed G, that is by definition f of f composed with f of G. And therefore, a map from BG to some BH, if we're now replacing this with normal notation, this is just f of fg equals f of f of g. This is just a homomorphism. This is a group homomorphism. And so a functor between these two weird group categories is just a group homomorphism. Okay, let's see what else we have. We have pi n, which is more of a homotopy theoretic one. There's a... Okay, cool. I guess homology is also a functor as well. We could say that. Okay, so we're nearly there. We just need to get through what a natural transformation is and what adjoint functors are. So, okay, unfortunately I've written in a bit of an... nearly fell over there. Unfortunately I've written in a bit of an unfortunate angle, but okay, we'll make do. So, natural transformation. So this is like maps between functors somehow, which again turns out to be useful in many contexts. So given two functors f and g are blah blah blah, we know that there's two functors. I don't need to write out all the information. We say that phi from f, and it's written with the implies arrow, to g is a natural, I'll just write nt. It's a natural transformation if for every c in our category is C. So these are both okay, I probably should have written a bit more information. These are both functors from two categories C to D. So we're picking an object C in C, and we're saying that the following diagram commutes. So we have a morphism phi C from f of C to g of C for every C, again for every object C, such that the following diagram commutes. We have f of C mapping to g of C via our map, and then we go down to f of D here. And this is just from some morphism, and then we apply the functor to this morphism. And again we go across here now. Now we're not going across via phi C, but via phi D to g of D. And then we go down again via g of f. So this has to commute for all C and D and F. So that's natural transformation. Let's see if I've got an example here. Oh yeah, a good one here, which you might hear this buzzword, natural isomorphism. God, talking is making me cough. Phi is said to be a natural isomorphism if phi C is an isomorphism for all C. So that's what that means. And again, I give a natural transformation, but in the context of homotopy theory here. Okay, I talk about equivalence of categories here, which is basically what you'd expect. We get another natural transformation, GF, and yeah, once we do F, hold on, what? Wait a minute. Oh, right, okay, yeah, so the natural transformations would be from FG to the identity. And if those natural transformations do exist, then we say that those two categories are equivalent, is an equivalence of categories. Right, okay. And okay, you can read the notice for a bit more detail about that. There is a result on equivalence of categories as well, but I am starting to wear away here, so I'm just going to get to the adjoint functors now. So thankfully this part is short and sweet. Okay, so two functors. Now this is not inverse, but it's kind of like inverse. we have two functors which kind of are in this, they're kind of relevant in the same area, but they just go the opposite directions. They're somewhat likely to be a joint, just somehow via mathematical magic. They just always end up being a joint. For example, the loop space and the suspension, they're just a joint somehow. Tensor and Hom, which we'll look at just now, are a joint. It's crazy. So yeah, if we have F going from C to D, and if we have G going from D to C, they're a joint if we have the following. So, if we do Hom D, Fx, Y, so if we go from Fx to Y, that's the same, that is, maps of this form are in bijection with maps Hom C of first going X, is it X? Yes, first going X and then Gy. So if we act with F on the left, that is essentially the same as acting with G on the right. For example, the tensor homojunction. Hold on, do I write? I don't think I've written out the proper notation for an adjunction here. That's alright, it's not too important actually. Oh, I have written the proper notation. Oh, excellent, it looks quite nice actually too. Tensor homojunction, now let me make sure that I do get the notation right, and this is the last thing I'm going to write, so I might as well write it in this lovely space. So we have this, and again we'll learn more about these functors in the next video. So you have tensor, what do I write here? X is from mod R. This is just the category of R modules. We have an adjunction, which is written with an arrow like this and an arrow like that. You can see it nicely in the notes, the LaTeX version. Like this, mod S, and here we have our guy Hom. From X dash. So, let's take a look at what this actually means. Okay, so, right, so, here we have f of x. Now obviously we've used x as a variable already, so we'll just say y here and we'll put z here. So, this means, and I'll write this in a different colour, this means that a map from the tensor product of y with x and then mapping onto z is the same, or is in bijection with, so corresponds to another map, mapping between just y, and then this y will map, an element of y will map to a to a map itself between x and z. So this is the tensor Hom adjunction. Now, yeah, I was a beast last year. I after talking about all of this, which has pretty much killed me, I then went on to talk about bloody colimits and all sorts of constructions. It probably took up the majority of that video, actually. Now here I've kept it short and sweet. I stopped here. This is quite a nice homological algebra fact. Yeah, geez, it's never really that pleasant to make just a full video on categories, but it is necessary. So hopefully you didn't really notice that it wasn't the most enjoyable video to make. Hopefully you learned something if you are here to learn about categories. And hopefully I'll be uploading my next video soon, which is on special modules, but I'll be talking about Hom and tensor at the start of that video too. So yeah, gregarious motivation, power through so that you can achieve your goals. I've powered through this video. Hopefully my phone didn't run out of battery. Thank you guys for watching, and goodbye.